The BIOS is a type of firmware used to perform hardware initialization during the booting process on IBM PC-compatible computers, and to provide runtime services for operating systems and programs. The BIOS firmware is built into personal computers, and it is the first software they run when powered on. The name itself originates from the basic input-output system used in the CP/M operating system in 1975, originally proprietary to the IBM PC. The BIOS has been reverse-engineered by companies looking to create compatible systems in the interface of that original system serves as a de facto standard. The fundamental purposes of the BIOS in modern PCs are to initialize and test the system hardware components, and to load a bootloader or an operating system from a mass memory device. The BIOS additionally provides an abstraction layer for the hardware, i.e., a consistent way for application programs and operating systems to interact with the keyboard, display, and other input-output devices. Variations in the system hardware are hidden by the BIOS from programs that use BIOS services instead of directly accessing the hardware. MS-DOS, which was the dominant PC operating system from the early 1980s until the mid-1990s, relied on BIOS services for disk, keyboard, and text display functions. MS, Windows NT, Linux, and other protected mode operating systems in general ignore the abstraction layer provided by the BIOS and do not use it after loading, instead accessing the hardware components directly. Most BIOS implementations are specifically designed to work with a particular computer or motherboard model, by interfacing with various devices that make up the complementary system chipset. Originally, BIOS firmware was stored in a ROM chip on the PC motherboard. In modern computer systems, the BIOS contents are stored on flash memory so it can be rewritten without removing the chip from the motherboard. This allows easy updates to the BIOS firmware so new features can be added or bugs can be fixed. But it also creates a possibility for the computer to become infected with BIOS rootkits. Unified Extensible Firmware Interface was designed as a successor to BIOS, aiming to address its technical shortcomings. As of 2014 update, new PC hardware predominantly ships with UEFI firmware. History. The term BIOS was invented by Gary Kildall and first appeared in the CP/M operating system in 1975, describing the machine-specific part of CP/M loaded during boot time that interfaces directly with the hardware. Versions of MS-DOS, PC-DOS or Dr. DOS contain a file called variously IO-sys, IBM BIO, COM, IBM BIO, sys, or DRBIOS. Sys. This file is known as the DOS BIOS, and contains the lower-level hardware-specific part of the operating system, together with the underlying hardware-specific, but operating system-independent, system BIOS, which resides in ROM. It represents the analogous to the CP/M BIOS. With the introduction of PS2 machines, IBM divided the system BIOS into real mode and protected mode portions. The real mode portion was meant to provide backward compatibility with existing operating systems such as DOS, and therefore was named CBIOS, whereas the ABIOS provided new interfaces specifically suited for multitasking operating systems such as OS/2. User interface. The BIOS of the original IBM PC XT had no interactive user interface. Error codes or messages were displayed on the screen, or coded series of sounds were generated to signal errors when the power-on self-test had not proceeded to the point of successfully initializing the video display adapter. Options on the IBM PC and XT were set by switches and jumpers on the main board and on peripheral cards. Starting around the mid-1990s, it became typical for the BIOS ROM to include a BIOS configuration utility, or BIOS setup utility, accessed at system power-up by a particular key sequence. This program allowed the user to set system configuration options, of the type formerly set using dip switches, through an interactive menu system controlled through the keyboard. In the interim period, IBM-compatible PCs, including the IBM IT, held configuration settings in battery-backed RAM and used a bootable configuration program on disk, not in the ROM, to set the configuration options contained in this memory. The disk was supplied with the computer, and if it was lost, the system settings could not be changed. A modern Wintel-compatible computer provides a setup routine essentially unchanged in nature from the ROM resident BIOS setup utilities of the late 1990s. The user can configure hardware options using the keyboard and video display. Also, when errors occur at boot time, a modern BIOS usually displays user-friendly error messages, often presented as pop-up boxes in a TUI style, and offers to enter the BIOS setup utility or to ignore the error and proceed if possible. Instead of battery-backed RAM, the modern Wintel machine may store the BIOS configuration settings in flash ROM, perhaps the same flash ROM that holds the BIOS itself. Operation System startup. Early Intel processors started at physical address 000FFFF0H. When a modern x86 microprocessor is reset, it starts in pseudo 16-bit real mode, initializing most registers to 0. The code segment register is initialized with selector F000H, base FFFF000H, and limit FFFFH, so that execution starts at 4 GB minus 16 bytes. The platform logic maps this address into the system ROM, mirroring address 000FFFF0H. If the system has just been powered up or the reset button was pressed, the full power on self-test is run. If Ctrl+Alt+Delete was pressed, a special flag value is stored in non-volatile BIOS memory before the processor is reset. And after the reset, the BIOS startup code detects this flag and does not run the post. This saves the time otherwise used to detect and test all memory. The post checks, identifies, and initializes system devices such as the CPU, RAM, interrupt and DMA controllers and other parts of the chipset. Video display card, keyboard, hard disk drive, optical disk drive and other basic hardware. Early IBM PCs had a little-known routine in the post that would attempt to download a maintenance program into RAM through the keyboard port before performing any other elements of the boot process, such as before scanning for option ROMs or executing a bootloader. If the download was apparently successful, the BIOS would verify a checksum on it and then run it. This feature was intended for factory test or diagnostic purposes, while it was of limited utility outside of factory or repair facilities. It could be used in a proprietary way to boot the PC as a satellite system to a host machine. Boot process. After the option ROM scan is completed and all detected ROM modules with valid checksums have been called, or immediately after post in a BIOS version that does not scan for option ROMs, the BIOS calls int19h to start boot processing. Post-boot, programs loaded can also call int19h to reboot the system, but they must be careful to disable interrupts and other asynchronous hardware processes that may interfere with the BIOS rebooting process, or else the system may hang or crash while it is rebooting. When int19h is called, the BIOS attempts to locate bootloader software held on a storage device designated as a boot device, such as a hard disk, a floppy disk, CD, or DVD. It loads and executes the first boot software it finds, giving it control of the PC. This is the process that is known as booting, which is short for bootstrapping. The BIOS selects candidate boot devices using information collected by post and configuration information from EEPROM, CMOS RAM or, in the earliest PCs, dip switches. Following the boot priority sequence in effect, BIOS checks each device in order to see if it is bootable. For a disk drive or a device that logically emulates a disk drive, such as a USB flash drive or perhaps a tape drive, to perform this check, the BIOS attempts to load the first sector from the disk into RAM at memory address 0x0000 0x7C00. If the sector cannot be read, the BIOS considers the device unbootable and proceeds to check the next device. If the sector is read successfully, some BIOSes will also check for the boot sector signature 0x55 0xAA in the last 2 bytes of the sector. Before accepting a boot sector and considering the device bootable, the BIOS proceeds to test each device sequentially until her bootable device is found, at which time the BIOS transfers control to the loaded sector with a jump instruction to its first byte at address 0x0000 0x7C00, CMBR invocation, and BBR invocation. Most, but not all, BIOSes load the drive number of the boot drive into CPU register DL before jumping to the first byte of the loaded boot sector. Note well that the BIOS does not interpret or process the contents of the boot sector other than to possibly check for the boot sector signature in the last 2 bytes. All interpretation of data structures like MBR partition tables and so-called BIOS parameter blocks is done by the boot program in the boot sector itself or by other programs loaded through the boot process and is beyond the scope of BIOS. Nothing about BIOS predicates these data structures or impedes their replacement or improvement. A non-disk device such as a network adapter attempts booting by a procedure that is defined by its option ROM or the equivalent integrated into the motherboard BIOS ROM. As such, option ROMs may also influence or supplant the boot process defined by the motherboard BIOS ROM. Boot priority: the user can control the boot process to cause one medium to be booted instead of another when 2 or more bootable media are present, by taking advantage of the boot priority implemented by the BIOS. For example, most computers have a hard disk that is bootable, but usually there is a removable media drive that has higher boot priority. So the user can cause a removable disk to be booted, simply by inserting it, without removing the hard disk drive or altering its contents to make it unbootable. In most modern BIOSes, the boot priority order of all potentially bootable devices can be freely configured by the user through the BIOS configuration utility. In older BIOSes, limited boot priority options are selectable. In the earliest BIOSes, a fixed priority scheme was implemented, with floppy disk drives first, fixed disk second, and typically no other boot devices supported, subject to modification of these rules by installed option ROMs. The BIOS in an early PC also usually would only boot from the first floppy disk drive or the first hard disk drive, even if there were 2 drives of either type installed. All more advanced boot priority sequences evolved as incremental improvements on this basic system. Historically, the BIOS would try to boot from a floppy drive first and a hard disk second. The default for CD or DVD booting is an extension of this. With the El Torito optical media boot standard, the optical drive actually emulates a 3.5 high-density floppy disk to the BIOS for boot purposes. Optical disks are a special case, because their lowest level of data organization is typically a fairly high-level file system. Reading the first sector of a CD-ROM or DVD-ROM is not a simply defined operation like it is on a floppy disk or a hard disk. Furthermore, the complexity of the medium makes it difficult to write a useful boot program in one sector. Even though optical media sectors are typically 2048 bytes each, 4 times the standard 512 byte size of floppy and legacy hard disk sectors. Therefore, optical media booting uses the El Torito standard, which specifies a way for an optical disk to contain an image of a high-density floppy disk and for the drive to provide access to this disk image in a simple manner that emulates floppy disk drive operations. Therefore, CD-ROM drives boot as emulated floppy disk drives. The bootable virtual floppy disk can contain software that provides access to the optical medium in its native format. Boot failure. The behavior if the BIOS does not find a bootable device has varied as personal computers developed. The original IBM PC and XT had Microsoft Cassette Basic in ROM, and if no bootable device was found, ROM Basic was started by calling int18h. Therefore, barring a hardware failure, an original IBM PC or XT would never fail to boot, either into BASIC or from disk. One model of the original IBM PC was available with no disk drive. A cassette recorder could be attached via the cassette port on the rear, for loading and saving BASIC programs to tape. Since few programs used BASIC in ROM, clone PC makers left it out. Then a computer that failed to boot from a disk would display "No ROM BASIC" and halt. Later computers would display a message like "No bootable disk found." Some would prompt for a disk to be inserted and a key to be pressed, and when a key was pressed they would restart the boot process. A modern BIOS may display nothing or may automatically enter the BIOS configuration utility when the boot process fails. Unlike earlier BIOSes, modern versions are often written with the assumption that if the computer cannot be booted from a hard disk, the user will not have software that they want to boot from removable media instead. Boot environment. The environment for the boot program is very simple. The CPU is in real mode and the general purpose and segment registers are undefined, except CS, SS, SP, and DL. CS is always 0 and IP is initially 0 by 7COO. Because boot programs are always loaded at this fixed address, there is no need or motivation for a boot program to be relocatable. DL contains the drive number, as used with int13h, of the boot device, unless the BIOS is one that does not set the drive number in DL, and then DL is undefined. SS, SP points to a valid stack that is presumably large enough to support hardware interrupts, but otherwise SS and SP are undefined. The boot program must set up its own stack, because the size of the stack set up by BIOS is unknown and its location is likewise variable, although the boot program can investigate the default stack by examining SS, SP. It is easier and shorter to just unconditionally set up a new stack. At boot time, all BIOS services are available, and the memory below address 0x004000 contains the interrupt vector table. BIOS post has initialized the system timers, interrupt controller, DMA controller, and other motherboard chipset hardware as necessary to bring all BIOS services to ready status. DRAM refresh for all system DRAM in conventional memory and extended memory, but not necessarily expanded memory, has been set up and is running. The interrupt vectors corresponding to the BIOS interrupts have been set to point at the appropriate entry points in the BIOS. Hardware interrupt vectors for devices initialized by the BIOS have been set to point to the BIOS provided ISRs, and some other interrupts, including ones that BIOS generates for programs to hook, have been set to a default dummy ISR that immediately returns. The BIOS maintains a reserved block of system RAM at addresses 0x00400, extension 004FF with various parameters initialized during the post. All memory at and above address 0x00500 can be used by the boot program. It may even overwrite itself.